Hey friends, welcome to the YouTube channel all about electronics, and today we will see the solved problems based on the magnetically coupled circuit. So now before we go to the problem, let's briefly understand what is reactance in the inductive circuit, as we are going to see this term many times during the problems. If you already know what is reactance in the inductive circuit, then you can skip this portion and directly go to the example 1 and 2. The timestamp link are given in the description below. So by clicking on them, you can directly go to the either example 1 or 2. So reactance is basically a resistance that is offered by inductor to the AC current. So this reactance is very similar to the what is resistance in the resistors in the DC circuits. And it is denoted by a symbol of X. And it has the same unit of a resistance, that is a ohm. Now this reactance is basically a ratio of voltage to the current, and it is given by the expression omega into L, where omega is the angular frequency and L is the inductance of the inductor. So as you can see here, as the operating frequency or inductance of the inductor increases, the value of this reactance increases. Now in case of a resistor, the voltage and current are in a phase, but in a purely inductive circuit, whenever the current passes through this inductive circuit, there is a phase difference between the voltage and the current. So whenever the current passes through any inductive circuit, the voltage leads the current by a 90 degree, or in another term, the current lags the voltage by a 90 degree. So if we represent this phase information in a A plus JB form, that is real plus imaginary term, then this reactance can be given as J into omega L, where this J omega L represents that the voltage leads the current by a 90 degree. So let us say if you have given one inductor which is having a inductance of 1 Henry, and if this inductive circuit is operated at, let's say, 5 radian per second, then the value of the reactance would be J into omega L, that is J5 ohms. Now if the same circuit is operated at, let's say, 10 radian per second, then the value of the reactance would be J10 ohm. So now as we know briefly about this reactance, so now let's move on to the examples. So here in this example, we have given one circuit which consists 2 inductors and a 1 resistor. And this circuit is driven by a 50 volt AC source. Now if you see this circuit, in this circuit, these 2 inductors are connected in a series and they are mutually coupled. And we have given that the power that is absorbed in this circuit is 168 watt. And in this circuit, we need to find the mutual inductive reactance between these 2 inductors. So first of all, let us assume that the current I is flowing through this circuit. So in this circuit, these 2 inductors are connected in a series and they are mutually coupled to each other. So let's say their equivalent inductance is X. Now here we don't know the value of this mutual reactance, and also we don't know whether this mutual reactance is additive or subtractive. So the value of equivalent series reactance would be either J5 plus J8 plus 2JXM if this mutual reactance is additive, or it could be a X is equal to J5 plus J8 minus 2J into XM if this mutual reactance is subtractive. But in general we can say that the total equivalent reactance is X. So the current I that is flowing through the circuit, which can be given as V divided by R plus Jx. That means 50 divided by this 10 ohm plus J into X. So the magnitude of this current would be a 50 divided by under root 100 plus x square, or we can write I square is equal to 2500 divided by 100 plus x square, and let us say this is the equation number 1. Now here we have given that the power that is absorbed in this circuit is 168 watt. Now the power always gets absorbed only across the resistive elements. So this 168 watt of power should get absorbed across this 10 ohm resistance. So we know that the power P can be given as I square into R. Now here we have given that power that is absorbed is 168 watt, and we know that the value of the resistance is 10 ohm. So we will get I square is equal to 16.8, and let us say this is the equation number 2. So now we got equation number 1 and 2. So let's compare this equation number 1 and 2. So comparing equation 1 and 2, we will get this equation, or we can write it as a 100 plus x square is equal to 2500 divided by 16.8. Now if we solve this expression, we will get value of x as approximately 7, or we can say that Jx is equal to J7 ohm. So in this way we found the value of Jx is equal to J7 ohm. So now if you see these two equations, the addition of this J5 and J8 itself is a 13J, and the total reactance that we found is a J7. So the total reactance has to be given by this expression, that is J7 is equal to J5 plus J8 minus 2J into Xm, or we will get 2J into Xm is equal to J6. So we will get value of this reactance is 3. So in this way we got the value of this Xm as a J3 ohms, and this mutual reactance is subtractive in a nature. So now let's see the second example. So in this example we have given two coils which are magnetically coupled to each other, and we have given that the inductance between this terminal 1 and 2 is 4 Henry when this terminal 3 and 4 are open, and when this terminal 3 and 4 are short circuited, then the value of the inductance that is measured across the terminal 1 and 2 is 3 Henry. So in this example we need to find the coefficient of coupling. So in the earlier videos we had seen that the coefficient of coupling K can be given as m under root L1 into L2, or in this case m under root LP into LS. Now in this circuit we had given the value of this LS, and first of all to find this coefficient of coupling we need to find the value of this LP and mutual inductance M. So to find these values we had given two conditions. So let's see the first condition. So in the first condition we had given that when this terminal 3 and 4 are open circuited, then the value of the inductance that is measured across the terminal 1 and 2 is 4 Henry. That means the value of the inductance that is measured across this terminal 1 and 2 is 4 Henry. Now whenever this terminal 3 and 4 are open circuited, so no current will flow through this inductor LS. So as no current is flowing through this coil LS, so there will not be any coupling on the primary coil or a coil LP. So whatever inductance that is measured across this terminal 1 and 2 is entirely because of this inductance LP. So the value of this LP has to be a 4 Henry. Now in the second condition we had given that whenever you short this terminal 3 and 4, the value of the inductance that is measured across this terminal 1 and 2 is 3 Henry. So whenever we short this terminal 3 and 4, the value of the voltage V2 will be 0. But now this current I2 will flow through this secondary coil LS. So now if you see, the current I1 and I2 are entering into the dots. So the value of this mutual inductance that will be generated in both the coils will be positive. So now let's apply a Kirchhoff's voltage law or KVL in the primary side. So we can write V1 is equal to I1 into J omega LP plus I2 into j omega into M, where the first term is the voltage that is induced due to this coil LP and the second term represents that voltage that is induced due to the mutual coupling. Let us say this is the equation number 1. Similarly, on the secondary side, as V2 is 0, we will get 0 is equal to I2 into j omega Ls plus I1 into j omega M. Here also the first term represents the voltage that is induced due to this coil Ls, while the second term represents the voltage that is induced due to the mutual coupling. Let us say this is the equation number 2. Now if we rearrange the equation number 2, we will get I2 is equal to minus M divided by Ls into I1. And we know the value of Ls is 2 Henry. So we will get I2 is equal to minus M by 2 into I1. Now let's put this value into the equation number 1. So we will get V1 is equal to I1 into j omega LP. Now we know the value of LP is 4 Henry. So that is j omega into 4 plus I2, and I2 will be minus M by 2 into I1 into j omega M. So now if we simplify this expression, we will get j omega I1 into 4 minus M square divided by 2. Or we can say that j omega I1 into 8 minus M square divided by 2. Now in the second condition, we had given that the inductance that is measured across terminal 1 and 2 is 3 Henry. So this term has to be is equal to 3 Henry. That means we can write 8 minus M square divided by 2 is equal to 3. Or we can say that M square is equal to 2. That means M is equal to root 2. Now we know that the coefficient of coupling K can be given as M under root L1 into L2. Or in this case, M under root LP into Ls. Now we know that the value of M is root 2, value of LP is 4, and the value of Ls is 2 Henry. So in this way, we will get a value of K as 1 by 2 or a 0.5. So in this way, we found the value of this coefficient of coupling as a 0.5. So I hope you understood how to solve these two problems. More examples based on the magnetically coupled circuits are given in the description below. So you can try to solve them by yourself. And if you have any questions while solving, you can ask me in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.